So thank you for the kind introduction. I sometimes struggle the last couple talks of a conference. So it's my colleague Bruno De Man and myself, and we'll try to make it interesting for you. I want to first of all point out that our colleague Eri Haneda did a lot of the work that I'm presenting here, but she's not here, and so I'm presenting really on her behalf. This is a collaboration with the UCSD, and I want to acknowledge our funding here from NIH. So the overall goal of what we'd like to achieve with this project is we'd like to make cardiac CT exams more robust, easier, and less prone to user error or non-idealities from variability induced by different users, and also make the scan faster and easier as well. And some of the things that make cardiac CT, so I also just want to point out that cardiac CT is a very important imaging technique, and recent recommendations have helped it to grow in popularity as well. So part of the struggle with cardiac CT, and the reason why we see some variability today, is that we need to ensure that we take the scan with optimal timing in terms of the contrast arrival in the coronary arteries, and that can be a little tricky. And another thing is that we want to ensure that we scan kind of at a more fine time scale at the correct cardiac phase in order to minimize the likelihood of motion artifacts. And ultimately, what we'd like to achieve with this project is to be able to do the prediction of both of these, the contrast level as well as the EKG signal, from sinogram projection data that's acquired, for example, a very small number of views per rotation in a monitoring phase. So before the actual scan, we would acquire one or two or a few projection views per rotation. And from those, from that stream of projection views, we would continuously update our estimate of the contrast level as well as the EKG signal. And then when we get to the right time, we would take the scan. So and I forgot to mention that this is done using deep learning. So we'll have a network for predicting the bolus level as well as one for predicting the cardiac phase. And so we need some training data. One of the challenges is that we would like to have this training data over a long time period as the bolus, from the bolus injection through when it peaks and beyond, so that we can learn the trends in the data. And also we want it to be very rich, many different patients, different orientations, different bolus curves, and so forth. And so we don't really have enough clinical data that fits the bill. And so we'd like to develop virtual projection data that we can use to train our model. So this is the framework, the flow of what we've put together. There's a first phase where we prepare our model, and a second phase where we actually use it to generate projections. So in the first phase, we reconstruct patient data that was acquired over at least a full cardiac cycle so that we can reconstruct every phase. And we reconstruct it every 70 milliseconds. So we have about 14 or 15 phases, that cover the cardiac cycle. And then for each of these phases, for each patient, we need a segmentation of some of the major structures. So for example, the 4 chambers of the heart, ascending and descending aorta, the pulmonaries. And we segment those objects, and we also label within each object sort of a blood flow propagation labeling that gradually increases along the direction of blood flow. We then digitally remove the contrast from these scans so that we get something that looks like a non-contrast cardiac scan. And now our model is ready to be used. when it comes time to actually use it, there's a series of user parameters. You pick a patient, acquisition protocol, heart rate, bolus curve shape, and so forth. And the model or the software takes the images with the bolus digitally subtracted and adds in according to the user specified parameters, adds in the bolus and propagates it through. And then we also do some augmentation. We do random rotations along the 3 axes, random shifts, random scaling, and we generate these virtual CT projections. And these are wide cone angle projections so that we can see the entire heart. So I want to talk a little bit about the manual segmentation. At first, we did this in a very laborious way, manually segmenting each of the 9 objects here in 3D for various patients in various phases. And once we had enough of the manually labeled data, we developed a deep learning network for doing this segmentation in an automated fashion. So in addition to just segmenting, just labeling these objects with one of these 9 labels, we also introduced the blood flow propagation labeling, which moves continuously, is a number that increases continuously even within a single object. So some objects had kind of a linear increase from an inlet to an exit point, and others had kind of a rotational blood flow propagation. Can't say that today. And this is done in 3D. We just showed this figure in 2D, but this is done in 3D, so we know how the blood propagates through each object. So this is an example of the blood flow propagation labeling. Here on the top, this was generated based on an analytical process from our segmentations, and then these were used to train a neural network that generated outputs that looks like this. So you can see the sort of bluer colors are the right side of the heart where the blood first enters after it's injected intravenously. The blood then goes out to the lungs and comes back later onto the left side of the heart and out into the aorta, which is, the ascending and the descending aorta have the biggest delay from injection. And so they show up as red here. This is the network that we used to do the automated multi-segment segmentation of those nine compartments in the heart. It also outputs the blood flow labeling as well. So there are 2 outputs at each voxel. It's basically a unit, and it uses a somewhat downsampled 3D image in order to, as an input. This is an example now of some of our simulated CT data. So we have a random, I mentioned that we have a random rotation, shifting, and scaling that's done for the purpose of data augmentation for our training, because we have only about 40 patients that we're using here to generate this data. And so we'd like to add some more variability. So this shows an example of a projection that we generated without doing any augmentation, no rotation, scaling, or motion. And then this one is the same patient with some rotations and so forth. So you can get the sense of what kind of transformations we're applying. You can see that things are a bit rotated and scaled in this lower image. This shows our bolus curve model. There are probably many ways to parameterize the bolus shape. We have a delay from injection to when the bolus first arrives on the right side of the heart. And all of these are random numbers that we generate within various ranges. There's a bolus rise time. We just use a cosine shape for the rise. There's a bolus height. There's opportunity to have a width, sort of a plateau at the peak of the bolus, and then there's a decay time and a final bolus level that might be above the initial level. This shows an example of the simulated bolus intensity over time. So you can see that the right atrium is the first chamber that the blood enters, and you can see the shape is very similar between the right atrium, the right ventricle, and the pulmonaries. And then we have some dispersion that we introduce between the left chambers and the right chambers. So, and that models the fact that, you know, some of the blood takes a shorter route through the lungs than other blood. You end up with a bit of a smoother curve on the left side, which you can see here, going onto the left chambers and the ascending and descending aorta. This shows the phase mapping. So I mentioned that we reconstructed our initial images every 70 milliseconds. What that means is that as we do our forward projections, we may not have a phase that exactly matches the one that we're trying to simulate. And right now we're just using a simple nearest neighbor interpolation. We just take the closest phase that we do have and forward projecting that one. So if you have a particular heart rate, there might be a series of phases that you want to forward project, as shown here by this kind of sawtooth pattern. I have two different sawtooths here for a 70 beats per minute case that we're simulating and a 40 beats per minute case. And you can see that there's a little bit of offset in some cases between the phase that we're trying to pick and the one that we're actually using, because we have only a finite number of phases reconstructed, but it's pretty good. So I would just want to show a couple videos of what these simulated projections look like. Going to, let's see. There we go. Yeah, so actually, this is not showing up very well at all. I apologize. But what you should be able to see is the contrast first showing up on the right side of the heart, and later you should be able to see the beating on the left side with the contrast flowing in. But that's obviously not working too well. I apologize. Okay. Okay. So here's an example of a real versus a simulated projection. So, and really I'm just showing that visually they look very similar. It's a little hard to see some of the details. So we also, we also, it's not working. Okay. All right. Oh, we're going to try that, I guess. So my apologies, please bear with me. Oh, well, I got the same thing. Oh, there we go. Okay. It's a very small file. I don't know. Okay, so what we had on the last couple slides, I'll just describe, and maybe it'll wake up here. But I had some difference images between the projections that we generated with the real projections as well as the simulated projections at different phases. So showing the difference between a baseline phase and other cardiac phases. And you can see good very good visual similarity between the simulated images and the true original images. Here we go. Oh. Ooh. So close. So I guess I'll just summarize. And we have now a five-dimensional model, so three spatial dimensions. You've got the bolus time dimension, as well as the cardiac phase. We can generate data that we can use to train our networks. And we've been developing two networks that we're going to use this for. One network takes in this stream of projection data, for example, one view per rotation, and continuously updates an estimate of the contrast in the left chambers of the heart and the right chambers of the heart. The other network continuously gives an estimate of the cardiac phase. And so we believe that this is going to lead to much more robust contrasts, better, on average, brighter contrast, or the ability to use less contrast with the same results, and also the ability to eliminate the EKG that's usually acquired during a cardiac CT scan. And there was a poster as well on Tuesday that talked about the bolus part, but so we believe that this is a early work. We're still working to improve the modeling of the bolus dynamics as well as the cardiac phase. As I mentioned, right now we just have that nearest neighbor model, and we're looking forward to testing this out with real clinical data. Right now, we've only tried it with these generated projections, but we feel like this is a good model that we can use to train our networks. So with that, I'll finish up, and I don't think you missed too many of my slides.
Thank you very much. Sorry for your technical problem. Any questions from the audience? Please. Then I will start. So the purpose of this particular talk is to develop tools so that later on you can use the tool to develop an algorithm.
That's right.
Do you have any concern that this deep learning based training tool has some limitation because you started with some kind of assumption, the bolus profile and heartbeat, heart motion pattern, and so on, all based on the assumption. And if that doesn't cover enough range, that develop using these tools would have a limited ability as well.
Yeah, I think that's always a concern. When it comes to any type of simulation that you're going to try to use, and later you're going to use real data. What we've tried to do to get as rich a data set as possible, with the augmentations, and we may need to add some additional richness to our bolus shapes to address that, the possibility that the bolus shapes may not match our model. But I think, as far as the cardiac motion, we feel pretty good about it. We're using the real cardiac scans from a variety of patients, and so we believe that those shapes are pretty good representation of reality.
Great. Any other questions? Please.
Thanks for a really interesting talk. I was wondering, so if the final goal is in part to estimate the amount of contrast which is actually within the coronary arteries, I'm wondering if you've considered like an analogous approach in which, instead of segmenting and considering the amount of contrast within the actual chambers of the heart, you've actually just directly tried to quantify contrast within the coronaries?
Yeah, that's an excellent question. The coronaries, I mean, the reason we look at the chambers is they're so much bigger than the coronaries. When you look at projection data, it's really, really hard to even find the coronary arteries. And the other thing is that the coronary, one thing I like to realize is the heart feeds itself first. And so as soon as the blood goes out the aorta, you have the coronary ostia, and the blood, there's not much delay between the blood that's in the left ventricle and the contrast that's in the coronary arteries. You may want to wait just a few seconds beyond the peak to allow that propagation to go down to the coronaries, but there's not much variation in terms of that very small delay between what's in the aorta and what's in the coronaries. So we feel there's a really good correlation there.
Right. If there's no other question, let's thank the authors again.